So, welcome all of you. My name is Attila. You and my co-authors are Lendvai, and we would like to talk about the numerical investigation of instabilities of steel members restrained by sandwich panels at elevated temperature. First of all, some kind of short literature review. Until this point, we had no information about the hackling restraining effect of the sandwich panels at elevated temperature. There were some experimental tests in the so-called EASY project, but now our scope was to define the effect of the elevated temperature on the hackling of steel members supported by sandwich panels. To be able to define this kind of effect, we had an experimental testing program when we had different kind of steel members. Now, in this case, in this presentation, we will talk about the compressed EGA sections, and we had panels with a size of 3 by 3 meters. We had this experimental test in the financial support of the Eurosteel project, supported by the RFCS. At the end of the day, we would like to define design method and guidelines for designing this kind of members. We have some slides about the experimental test to be able to understand what was the case, what we examined. You can see here the testing tool. The main member was here, and we had the panels, the 3 by 3 meters. We applied forces on one side from here, and we have some kind of supporting members to support the panels. Of course, these were connected with hinge and hinge connection to be able to get the formations. So in this test arrangement, we had various sections as the main members, age 120, 160 sections, and cold roll HHS sections as well. And we had different adding systems as well. You can see on the right side in the table that we had panels with PRIR core. We had a mineral wool core, and we had trapezoidal sheetings as well. And all of these tests were carried out at ambient temperature, at elevated temperature. We went until 300 Celsius in this case. You can see some pictures of the test. Here we applied the temperature load by ceramic heating pads. you can see the arrangement of the heating pads here on the right side, and we assume that the hammer itself was protected against the fire load, so we applied lower temperature there. We measured, of course, the temperatures of the hammer. We measured the temperatures on the cladding on both sides, the exposed and unexposed side. Of course, we measure the displacement of the hammers, the axial one, and then plane it out of plane deformation at the height point of the member. Here the axial displacement, and of course we measure the applied load. Here you can see the typical failure modes. Here the flexural buckling of the member, and some kind of additional failure modes, hole elongations, local buckling of the sheeting as well. The screw deformations can be seen here, and the lamination of the sandwich panel can be also seen here. We shown here the force deformation diagram. As you see at the beginning of the curves, we have some orientation of the pin and the nest at the end of the hammers, but otherwise you can see a nice force deformation curve for various temperatures as well. Here you can see on the next slides some pictures of the highlight element model. The panel itself was modeled with volume elements. The eye section was modeled with shell elements. We defined the gap between them, and we applied contact elements between the panels and the eye section, and the screw was modeled with spring elements to be able to follow the behavior of the screws as well, and we applied the axial load as the same way as we used in the experimental test. We carried out hash sensitivity calculation. You can see the curve various hash sizes, and we define the final mesh size to compare the results at the end. The temperature load was applied by its effect, so we changed the material properties of the steel and the panel as well, so we decreased the yield strength, and we increased the spring stiffness of the screws as well. With the other presentation about this as well. You can see the failure modes after the simulation. Of course, we did a time history analysis in this case, and you can see the flexural buckling of the main member on the right side. You can see the comparison of the various cases. You can see it, and it's kind of strange, but due to the heating load or temperature load, we have this kind of not so straight curves in some cases. Well, the finite element model shows a very nice temperature dependent behavior. You can see in this table that what is the degradation of the degradation of the ultimate load according to the increase of the temperature. We can say that we have better fit between the finite element models and mineral cladding case, but we have not so good agreement in the peer cases, because in that case at an early temperature the eliminations started in the experimental test. So it's definitely needed a further investigation in the peer case, where we have to take into account the denomination of the panels. But we can say that the finite element model is applicable to follow the general case experimental test results. So we would like to thank the financial support of the FCS program. It's called SAPFI in this case. Thank you for your kind attention. If you have a question, please don't hesitate to ask. Thank you. Bye.